As Alan said, we're really a system solution provider. We have a wide array of product lines. Some of you may know me from working with your electrostatic precipitators. Brian Buchanan was in charge of the process bearing material handling division for many years before moving into his role. And of course, Alan is oversees the air handling. So we really offer a big array of product lines as well as turnkey solutions, including inspection, service, maintenance. And just recently, about 2 years ago, we significantly increased the amount of business we do in Canada with the incorporation of our Canadian entity here. We have a big 2 large shops and fabrication facilities in Pelham, Alabama. Not sure, Brian, maybe anything else to add on the background of our company? Well, I'll let you direct me moving forward on going to the next slide, okay?
All right, let's go to the next one. Guys, this is just a lot of the different companies that we deal with. They are, not only are we in the pulp and paper industry, we're also in, as you can see, the cement business, the steel business. We do KO and we do power generation. We do petrochemical. We do garbage burning facilities. Just about anywhere where there's a stack, there's going to be our equipment somewhere around it or at the bottom of it. We do a lot of work in the power industry now. We kind of grown into that. A lot of customers there from Energy to PacifiCorp to TVA, Basin Electric. All right, next slide. And what makes us unique is that we do feel like we can do the total solution. We're not only can we do the engineering part, we can do the supply of the equipment, and we can also do the installation. And that's kind of what this slide's trying to drive home, that we're total solution provider. We do, like we're talking about, we're going to talk mainly fan work and new fan designs and the upgrades around new fans, whether the upgrade be a mechanical type upgrade or a performance type upgrade. And we'll talk some both of that in our presentation. We do the auxiliary equipment around that, dampers, expansion joints. We do dust collectors mainly mechanical collectors. And we do those really for the biomass business, for your power bore, because what we normally see is we see an ID fan that's behind the dust collector but in front of a bag house, and there's a reason for that. You want to keep a positive pressure bag house to minimize, if not prevent, fires. If you go strictly on the back side in that situation, you're very likely to get a bag house fire and burn your bag house down. And we do that work around it. We do, fan repair and complete redesign of fans, as well as just rebuilding and building kind. Our goal is to service our customer. All right, next slide. And this is just an overview of material handling. We're not going to get into this, but just we want to make y'all aware we do solid fuel systems and ash handling systems. All right, next slide. And we do, like we talked about, we do the field installation work that we use in conjunction with our fan equipment. And we have a whole, what we call a technical service group. And this is a group of engineers that do beyond just fan balancing. We do vibration analysis, modal analysis, we do startups, we do PM, preventive maintenance, we do technical assistance. So there's a lot we do out of that group. All right, so now let's get into the meat here. Next slide on. In your environment, there's going to be typically you got a biomass borer, power borer, combo borer, bar borer, and it's normally got, combustion air fans or forced draft fans. You could have a BFB or a CFB, so it's got a fluidizing fan possibly. Then there's normally a fan that's over the fire in some way, or the OFA fan. The undergrade fan is normally what we call a forced draft fan, but it's going to be referred to as the undergrade. And then you normally have fans on the back side or toward the air pollution control, which are the ID fans. And there are occasions where we see booster fans where there's been some kind of APC added that required an additional pressure, and there may be a very high volume, very low pressure fan on that. All right, next slide. And then also in your meals, normally we would have a chemical recovery board, and the fans in that are normally the primary fan, primary air, secondary air, tertiary air. Every now and then we'll see a fourth level of air, quaternary air fan, and it's rare, but I've seen them to where there's literally 4 levels of air. And then on the back side, you have the ID fan and possibly a booster fan on a recovery board. Normally what you're dealing with on the next slide, go ahead. Normally what you're dealing with on the recovery board fan is salt cake. And then there's that lime kiln fan or that chemical recovery kiln fan. Probably the hardest fan in your whole meal. They routinely get built up on them. They have vibration issues, cleaning on a routine basis. They're normally oversized, and it makes them difficult to control. And they're just a whole host of problems. And we do a lot of work around lime kiln ID fans. And the theme of what I want to talk about is it takes more than good fan equipment to make a good fan installation. You can have the best equipment in the world, and if you don't have all these other things that go with it, and we're going to go through them, then you probably may have issues with your fans, and it's something we can talk about. All right. So the first step is that you want a properly applied blade design. Next. In our business today, we normally have 6 different types of blade designs. From a radial blade design all the way to an airfoil, radial blade, forward curve, radial tip, backward flat, backward curve, and airfoil. They normally go from the cheapest in the upper left-hand corner to the most expensive in the right-hand corner. But they normally go from the least efficient to the most efficient. And they all have their place. And we're going to talk through each one of these. All right, next one. On the radial blade design, it's the oldest one in the stable. Started building these in the 50s. Low initial cost, straight blade, just by the nature of the way they're built and their design, they're self-cleaning. It's hard for material to stay on that blade because of the centrifugal force. They're really easy to put on abrasive surfaces and corrosion. They're easy for corrosion environments because with them being straight blades, they nest well. So they're actually a very good fan if you're looking for something in a very abrasive, very corrosive environment. Structurally, they're very strong, very maintainable, very dependable, very reliable. My next slide. The downside, like we talked about, is they have the lowest efficiency. They're noisy. Your efficiency loss is normally in noise and heat. And so they're not very efficient just by the nature of the blade. Next slide. This one here is a forward curve design, and you won't see this much in mills anymore. The place where I've seen them the most is the recovery borer ID fans. They've got advantages in the fact that they have what we call a high SP to PVP ratio, which means you can stuff a lot of fan package in a very small area. They're quiet, they're smooth, still light, in a lot of places where they're used, you normally find them on the 5th or 6th floor of a borer house. Reasonably efficient, 72 to 76. You'll find these in your Gen Air systems, that are over your oven or stove. They're in your air conditioning units because they just. I'm sorry, what now? Can y'all still hear me?
Yeah, I think it was some background noise. There is a question, Alan, from Ian Granger.
Okay.
Ian, yes, sir.
Well, at our mill, we have 2 flash drying lines. Each 3 is radial fine. Like somebody told me we call them. So decade in service or so, and then the blades they erode away, and almost. So I was just wondering what the best repair thing is. Like, can you weld plate over those blades, and then make I guess the blade is a little bit thicker then, or anyways.
Which type of blade do you have blade design? Do you have a radial blade?
Sorry, what was that?
Do you have a radial blade fan, Ian, or is it a forward curve?
It's a radial one.
Okay. Yeah, the answer is yes. I mean, you can put wear pads on it. I would not advise you to do it just in the field though, without some assistance, because when you go to start welding on to an existing fan, you're adding weight, which means you're adding inertia too, which can give you starting problems. But adding weight, you're adding, stress to the existing structural components. So I'm not saying you can't do it. I'm saying if you do want to do something like that, you should get a fan OEM involved. And we put wear pads. We put wear pads and do build up on your type of problem all the time, to where it's a constant cycle.
Okay.
All right.
Well, I don't want to take up too much time with that question, but yeah, we need to figure what's the best repair method there for the erosion that creates gouges in the blades, and we're worried about, them cracking and then coming apart, and then with not good consequences. But
I get it.
All right, thank you.
Yeah, we can talk more about it once we get out of this.
Yep.
All right, the forward curve, of course, the disadvantage is it's a real antiquated design. I've done this, like I said, for 40 years. I've sold 2 forward curve fans as new fans. We do rebuild a lot of them. They're very suspect to build up, though, very structurally weak, where a lot of fans we can run in the high 20s and 20,000 feet a minute. Even in some of our backward curves and radial blades, we can run close to 40,000 feet a minute. With a forward curve, we can run about 16,000 feet a minute. So it's a pretty weak fan. And it's hard to put wear pads on. You can. I mean, you can flame spray it or you can coat it with tungsten, but it's just not a good design. Next slide on. Moving up, the next one's a radial tip. It's the next best fan you have that would self-clean. It's probably what you would find in as your ID fan. If you got a dirty ID fan on the back side of a biomass bore, probably what you would find on your recovery bore as well is a radial tip design. They're fairly efficient, 72 to 78%. They have a lot of the characteristics of a radial blade fan. They may not clean quite as well because they do have that back side, but the way it's shaped, supposedly it self-cleans itself. All right, next slide. The downside is, of course, the efficiency. We can get up to 79%, but when you do that, that is a fan that's really laid back. The blade's laid back. So it becomes, the more the blade lays down, the more susceptible it is to build up. So you have to be careful there. It has some noise issues possibly, and to get these high efficiencies, it normally has to have a very large housing. All right, next one. Now this is kind of the universal fan of today, the backward curve design. We say it's cheap to keep. So I mean, if you evaluate it out against the other designs from a capital cost and operating expense, the backward curve would prove to be your best choice. That's why we talk about low evaluated costs. It's smooth operating, has a non-overloading brake horsepower curve, and the fact that it peaks out at some point in its volumetric range, and that way you can size a motor that'll never not be large enough for what you need. It is a good high efficiency corrosive alternative. Efficiency is up to about 82%. It's a really good design. We use it both in ID and FD service. The downside is it's more expensive to build normally than an RB or an RT. With the blade being laid down, it has what we call a lower SP to PVP ratio, so it takes a larger wheel to produce the same specified pressure as it would take that radial blade or that radial tip. And they can be weak because sometimes they get to be very wide. This picture in here is one that is a center plant and a steel mill, and it's a heavily armored fan. That's chrome carbide all over that fan, and it's about 160 inches in diameter. And it's a really tough environment, but we would see this on either most of the time they're used as an ID fan service. Most FD fans, if you get to choose, are going to be more there for next slide. Now the backward inclined flat is the cousin of the backward curved, just not as efficient. And it's not as likely to build up as much because it doesn't have that cup on the back side of the blade. But otherwise, it has just about all the other features that a backward curve would have. And we would use this when there would be like a moderate chance of buildup. We would go to a flat blade. We don't sell a lot of flats. We've gotten very good at being able to keep backward curves clean. It is a great alternative, though, in corrosive environments because having that flat blade makes it nest well. Very easy to armor because you can put some really heavy wear pads on it that, they're being flat and without curvature, make for a great choice. All right, next slide. Downside is the same as what we talked about with the backward curve. Can be suspect to build up, limited pressure, strangely weak, and they too cost more, but not near as much as the backward curve. All right, moving on. And now we get to, this is by far the best choice. If you can use an airfoil today, you should. the highest efficiency available, much improved over our RBRT designs. They are very quiet in operation. If they're sized properly, they're smooth operation, non-overloading, and very superior in strength because that blade has a section modulus as compared to a single surface blade of a backward curve. We can get efficiencies up to 88% with this type of fan. Here's some examples. I'll let Ivan thumb through them. Now the airfoil though does have some disadvantage in the fact that it's a hollow blade, so it can, you can, if you got a wear environment, you can penetrate that blade, and then normally you won't penetrate them all at the same time in the same way. So the material will build up in one blade along, and you'll wind up with a heavy spot, and you'll wind up with vibration problems. They can tend to build up. I would never recommend them in a really moist, moist environment, like a scrubber application or something like that. It's just it's a recipe for a disaster. They too, because they have a lower SP to P ratio, it's a bigger wheel normally. Okay, next slide. Here's an example of a very large one. This is a Booster ID fan that we did. Big, it only runs like 705 RPM, but it's about 160 something inch diameter wheel. And this is the housing that goes with it. My safety group hates when I put this picture up because we're not tied off, but it represents the size of that housing relative to that fan wheel, that rotor. Just another example. All right, now we're back to this where we started, and these little numbers down below each of those fans, they represent kind of the efficiency that fan would achieve. And you can see it goes from 72% on the radial blade up to 88% on the airfoil. And he might, why is he telling me all this? Next one. All right, next one. This is why I'm telling you all this. Efficiency is very important today. And so as you see that E sub S number in that, I'm going to show you many equations, but this one's important. Q, that E sub S in the bottom is what we're talking about, that number. And Q is flow rate, P sub S is pressure. K sub P is a compressibility constant. K sub P varies on a fan from about 0.9 to 1. The more pressure you have, the lower the K sub P goes. That's constant, 63, 62. This just gets all the units in order, and that's what that is. And then you have that E sub S number. As that E sub S number goes up, that horsepower goes down. And that's what this is all about. So at 88% for an airfoil versus 72% for backward curve, you can tell it's a big difference in brake horsepower. All right, next one. And so this is kind of a relative comparison. If it costs me $1, and it can be a Canadian dollar, guys, if it costs me $1 to run a radial blade fan, I can run that same fan in that same capacity with an airfoil for 82 cents. Now, the numbers shown here are US, and this is a little bit old. The 7 cents a kilowatt hour is the national average here in the US. It's higher today. It's more like 9 cents a kilowatt. So you can see you can save about, well, today would be close to $600 per horsepower per year. It gets to be a lot on these fans. All right, next one. And just in the US alone, I wish I'd have done one for Canada. I don't know if I could have got all the stuff, but you can see in some of these areas, power is very expensive. Like out on the West Coast for us, power ranges up in the 20 something at 14 cents to 20 cents. Alaska, it's 33 cents. Hawaii is up in the 30s. So, and there you see down in the right hand corner, 9.4 cents per kilowatt hour. And that's real money. So now we'll talk to you a little bit about, we're gonna come back to this efficiency, but kind of thumb through the topics here. Talk to you about fan speed. Most of your ID fans that you're going to deal with, if they're on the dirty side, they're probably running 900 RPM. They're probably a medium pressure, medium to high volume, and they can be dirty to very dirty. And then your other ID fan, if it's on the clean side, say it's downstream of a baghouse or an ESP, it's probably going to run 1200. That's where it can run. That's where we would select it today. Most of your FD fans today, depending on the end user, are going to run either 1200 RPM or 1800 RPM. There are some small fans out there that people choose to run 3600 RPM. That's not what I would do. I tell people I've got a lot of experience with 3600 RPM fans, and it's all bad. It's not the fan equipment, it's the bearings. It is very hard to keep bearings lively to live for a period of time at that speed. And then the bottom one down there is 720 RPM. That's only a booster fan or some very dirty fan. So speed's important, and honestly, the slower you can run, the better off you are. Anybody have any questions? I've been talking. All right. I want to go through a fan curve because people see them, but I'm not sure they know how to read them all the time. So if you do, forgive me here. This is the basic characteristic curve here. This is static pressure on the left, plotted against volumetric pressure at the x-axis. And this is a very typical fan curve. All right, go to the next slide. And then this is the typical horsepower curve that goes with it. And you would read the horsepower on the right as compared to the volumetric flow rate on the x-axis. Very typical. And this is, back up just a little bit, this is a non-overloading curve that I'm showing. That's non-overloading. See, it has a peak. And if you size your motor, you can size your motor to where you'll never overload your motor, no matter how far out you go in the volume. All right, next curve. All right, this is the static efficiency curve. And if you see, it peaks out just to the right of the peak of the characteristic curve, or what the static to volumetric curve. And that's why the selections are made just to the right of the peak of the curve and down slightly, because it's a stable point of operation. Right, next curve. And here is the system resistance curve. This is static pressure plotted against volumetric flow rate. This is what your system requires for the amount of pressure that the amount of volume that you're trying to put through it. The more volume you have, the more resistance that you will have. And that design point up there, that is where we're designing your fan. Go to the next slide now. That is where we're designing your fan, where the system resistance curve meets the fan characteristic or performance curve. You'll hear people say, well, I'll give an example. I've got 100,000 ACFM at 10 inches. Well, that's that point of rating. And that's that point on the system resistance curve where there's 100,000 ACFM and it requires 10 inches to drive that through your system. And that intersection point is what you're selecting for. And if you were to read this curve now, that point of rating, and you wanted to read the horsepower, you would move straight down, you would find the point on the horsepower curve right there, and then you would go to the right and you would read that horsepower. And then if you wanted to read the pressure, you go back up to the point of rating and you'd read that pressure that's on the left side of the curve. So fan guys love to draw these curves and it becomes confusing and doesn't need to be. And then your sweet spots, there's two lines drawn on there. That's normally where you want to make that selection for that fan. And you want to make it such that you're far enough down the curve to the right of the peak of the curve that it's stable in operation, but you're still, if you read down, you see that blue line, that's the peak efficiency. So you're at maximum efficiency, and that's a point where you want to select a fan. Right, next curve. Right, to understand the system resistance comes in basically two forms. You have a big system resistance. In other words, the system doesn't change. Well, that pressure drop through that system varies by the square of the volume change. It's really varying by the square of the velocity change because of the frictions that are involved in the skin frictions on the ductwork, and then also in the changes in area and the elbows and changes in direction, and then the equipment it goes through. All right, next slide. But you also can have a component which is a variable system, which would have a constant pressure drop no matter where you are volumetrically. The reality is you got a system resistance, go to the next one, that is the combination of the two, and they're additive, and that's normally how a combined system resistance curve looks. So if you can come up with that system resistance curve, I can design you a fan all day that operates great. That's the problem with new systems, though. It's somewhat of a guess to begin with, and so you may miss it. And go to the next slide, Bob. You don't want to miss it, though. Fans need to be right size. We used to see years ago that people did not want to be fan limited. They didn't care. I don't want to be fan limited. So they would go to an A&E and the architect engineer would oversize the fan. He'd write some elaborate spec that was going to crucify the fan vendor if he didn't meet that performance. So he'd oversize his fan. There was already margin on it anyway. And before you know it, you had margin on margin on margin. You had a fan that was oversized, and now the fan was wanting to operate further out its fan curve or be dampered. And that led to an inefficient design. So fans need to be right size. And if you ever get the opportunity to actually test your fan, and you're going to reevaluate your fan, and we're going to talk some about this, going to a upgraded fan, it can save you a tremendous amount of cost and power, and power's money. All right, next one. So these are just typical fixed system resistance curves. And the reason I'm showing you these is you want to operate up in that sweet spot. But if you've oversized your fan, you can very well get down where you're operating further and further out to the right of the curve. And I wish I'd drawn one other curve on this. If you remember, there's two types horsepower curves. There's non-overloading, and then for a radial blade and most RTs, it's overloading. Well, if you miss your point of rating and you're way out your curve, there's a good chance you become motor limited and can't even get to what you really need because your fan is so mismatched to your system. All right, next curve. We'll talk some about bearings because they're next to wear or next to corrosion. Bearings will give you more problems than just about anything. Commonly used sleeve bearings are Dodge or Ring. Theoretically, they have an infinite life. They don't. A lot of companies used to do elliptical bores. Everybody seems to be going back to, it's funny, it's like a pendulum. I've seen it swing two different ways in my lifetime. But everybody's tending to go back to cylindrical bore bearings, and the reason they are today is they're stiffer. And most people in the maintenance side like the sleeve bearing because it has split liner. And just to get down to the crux of what I want to talk about, the killers of a sleeve bearing are lubrication, contamination, and loss of external cooling. So, you know, in your environment, what you want to do is make sure your external cooling can be maintained. Try to keep seals or even auxiliary seals. We can put on auxiliary seals on your bearings and check your, oil. And most of you may do this, where you check your oil on a routine basis just to be sure you're not getting contaminated. On next slide. The other, bearings that we see are anti-friction bearings. Mainly we see spherical rollers. The bearing manufacturer would tell you that you needed 100,000 life hours. I would tell you that we would never design a fan with less than 250 to 3. A lot of people want to use split designs in this. That's fine, but you do realize you're giving up normally life for a split design. It comes with a cost. They don't have as high of rating as a solid, race design. Same thing's wrong with this. The speed limits, improper insulation, and mainly lubrication. It's not just lubrication contamination, it's over lubrication. I grew up on a farm and I understand what over lubrication is. We used to grease our bearings until the grease ran out to seal. That's not what you want to do. You want to get in and listen to the OEM bearing manufacturer and grease those bearings according to what the fan guy says and the bearing guy says. All right, next one. And here are the different types of antifreezens. Single row ball, angular contact. Single row ball, you just about can't get any thrust on that bearing. Angular contact ball bearings, you can get a little bit of thrust. Double row ball bearings is what we predominantly use there on the right, and we're using those normally on the free bearing and on a lightly loaded situation. On next slide. And then there's the other, what we normally use is the spherical roller bearing, and it's normally used on the fixed side because of the spherical rollers. It can carry thrust. And it can be a split ring design or a solid ring. But there's also, those cylindrical rollers out there. They're not what I would recommend because they have very limited thrust. The only thrust surface is really the end of the roller itself. And then there's the tapered roller bearing is a very unique bearing. If you've got a very, very high thrust with almost no radial load, you would use this bearing. It would have a place, but 90% of the time, you're going to be using spherical rollers. And if you're not too lightly loaded, you're going to use it on both sides of your fan or both bearings. And if you are, normally your free bearing would be a double row ball bearing. All right, next one. Your other problem around fans can be your couplings, and probably most of the couplings you have today are either gear couplings or grid couplings. There are becoming the advent of more VFDs, and we'll talk about that a little bit, but probably the workhorse of the whole industry is the gear coupling. And as long as you maintain that coupling, it should last a very, very long time. The wear on the teeth should be minimum. Where we see you lose the gear couplings is misalignment, and a lot of people do. But that's fine. A lot of people like non-lubricated couplings. We see the dispatch mainly in petrochemical business or where there's some very, very cold environments. You might see that. And the last one down in the right-hand corner there, that elastomeric coupling is what we use mainly on VFDs, variable frequency drive. They can be tuned for the torsional vibration and torsional natural frequencies you might have. They are somewhat of a higher end product, can be a little bit pricier, but they're zero maintenance. And the only thing you would do every few years when you change out a fan, if you ever do, you would change out the rubber grommets in it. All right, next one. There's always a question about whether I use my inlet dampers or outlet dampers for control. Never, ever use outlet dampers for control if you don't have to. Use inlet dampers. Outlet dampers are nothing but a pressure drop. So they're part of the system. Whereas an inlet damper can give you pre-spin into a fan and lower and help improve the efficiency in a dampered situation, lowering the power requirement. An outlet damper is strictly a pressure drop, and it's a loss. So always, and the type of dampers you have inlet box. Go back when you have inlet box dampers, they would be the ones that are labeled the inlet box parallel blades. That way you can pre-spin the gas into the eye of the fan. By pre-spinning gas into the eye of the fan rotor, it unloads the fan ability to transfer mechanical work to the gas stream, and it actually improves your efficiency. And then the other one is the VIV, or the radial type that you see there in the middle. Can be a pancake style, or it can be built into the cone. All right, go to the next one. And damper curves are, this is what a typical set of damper curves are like. And we're drawing the system resistance curve on there as well. So as you go down in performance requirements, less volume means less pressure requirement. You kind of follow down the system resistance curve and you would land on some of these damper curves. Right, do the next slide. Conversely, if you got an outlet damper, it's straight up. It's just part of the system, and you're not altering the fan. You're altering the system. So as you damper, you're just going further and further and further out the fan curve. That's all you're doing, and dropping pressure. And here's some examples. This is the variable inlet vane we were talking about. This one built into an inlet cone. Very efficient design. You can get an improvement of about 3% over the use of a multi-louver parallel blade by using this style, but I would not recommend it in a dirty environment. So, all right, next. Now this is the multi-louver. This is what we would use, like the VIV we would use on an FD fan. The multi-louver parallel blade we would use on an ID fan. And the reason is we can keep all the linkage and bearings and everything outside of the gas stream. All right, next one. And then if you're using a damper in your system itself, we would recommend a multi-louver opposed blade. That way the flow coming through the damper is straight or laminar as compared to pre-spinning in the fan inlet box like you would want. And this is a typical opposed blade damper. And then there's always the question of variable speed today. I would use variable speed if you can get a return on investment every day. And normally that's going to depend on what you're trying to control. If you got a fan that is base loaded and rarely moves, you may not can get the return on the investment. But if you're doing wide swings and sometimes you're dampened quite a bit, VFD makes a lot of sense. It is controlling a fan with speed versus dampers is always going to be more efficient. You just got to make sure the economics work out, that you're actually gaining something by investing in that variable frequency drive. All right, next slide. Of course, every fan needs to be balanced. When it leaves our shop, we balance to this standard, ANSI S2.19. G.6.3 is fine for fans, but most people are not satisfied with that today. So we see a lot of G2.5 and even some G10. Let me give you though kind of the comparison. The G1.0 is what they would balance the drive in your computer to. G2.5 is what they would balance a large electric turbine to, running, whatever, 3,600, or even some like turbine in a jet engine that runs 6,000 RPM. G6.3 is what was set up for fans, but a lot of people want a little bit better. And all this standard is, go to the next slide. I think there's an explanation. All of this standard is set up to allow the balance to be independent of the foundation. You can have a great foundation, well made, and of course, if they don't balance your fan, you're going to get vibration. conversely, you can balance the fan down to very little residual unbalance. Put it on a very weak foundation, and you'll get a lot of movement. We used to see years ago, well, I want my fan balanced down to 1 mil. Well, that was very subjective because your system, your fan foundation system is just as much a part of that as balancing the fan down itself. And that's why, it takes a good foundation to make a good fan installation. On next one. We were talking about wear earlier, and wear is a major problem. And we address wear, we may go through generations of fans where we make improvements. And kind of the way it goes is here's some of the wear solutions. You can use same material as a parent material, and it kind of goes from the top of the list to the bottom of the list as being the least expensive to the most expensive at the bottom. Today we use a lot of kind of middle of the road, the chrome carbides and the complex carbides that are overlays on mild steel backings. And that's probably what we would see in your environment, say on your ID fan on a biomass board. Is more of a chrome carbide, or possibly even the second line there, a Quinson tempered low steel AR plate, which would have a, we'd call it AR 400, 500 per nail, whereas a chrome carbide overlay would have a 750. All right, next slide.
Alan, there is a question
Okay.
from Srinivash. I'll put it up here. Will there be an effect to power consumption when we change coupling type from flange gear to grid coupling? Can grid couplings be used for a fan without VFD?
Absolutely. A grid coupling can be used without. What a grid coupling does, it allows you to more or less alignment. Now, grid couplings are a little better than gear couplings when it comes to VFD. Today we'll use a grid coupling up to about 1,000 horsepower on a VFD installation, and then we'll go to the elastomeric. Never use a grid coupling on a VFD. There's always that little bit of torsional chatter, vibration, and it'll wear the teeth off. Won't be as bad today. It used to be real bad. VFDs have gotten so much better because they're anywhere from 12 to 24 pulse machines today. That's how they make a VFD. It's a bunch of little step functions that assimilate into a sine wave. And to answer your other part, you're not going to get an improvement in efficiency by changing your coupling. I believe that would answer it.
Very good. Thank you, Alan.
Next thing is takes, to make good fan equipment, we've talked a little bit about it, takes a well-engineered foundation. Foundations, and we say this all the time, we see where young engineers today will size based on what they learned in school, and I don't blame them. And it's designing a foundation for a fan. It's not about allowable stress. It's about deflection. You're wanting to control the amount of deflection. And here are some rules, 7 to million pounds per inch. It's kind of in the vertical, and 5 million in the horizontal pounds per inch. We'll put this on our drawing, and people who are really trying to design their foundation will call us and say, "You're crazy. We can't do that." Understand. But now that we're talking, we're going to help you design a good foundation. So these are some of our recommendations. If you're looking to design a foundation, I can provide you with a list that's about 4 pages of generalities. Foundations need to be either stiff and stable soils, good pilings, good casings. It starts there. And then you need to have beefy piers that limit the amount of deflection and have ample dampening. That is critical to good foundations. Next slide. You got to have a good grout area. So often people will build a wonderful foundation and then they'll use masonry grout and hard shims. Please don't do that. On any of your dynamic parts, invest. Use epoxy grout under your bearing pedestals and also under your motor rails. You'll be glad you did that. And you want to set them by using jacking bolts. You don't want to use hard shims. I'm not opposed to using masonry grout on housings if that's what you want to do, but by all means, put them on hard shims if you're going to use the masonry grout there, because you will be replacing that grout. If you use epoxy and you do it right, you'll never have to replace it. All right, next. Around the fan too, it's important you have a well-designed product system. And we see a lot of times where people I just absolutely ruin their fan performance based on their inlet and outlet ducts. Fans you don't need to have radical turns or transitions on the inlet or the outlet of the fan. And you don't want to have ductwork that's oriented such that it reverses the flow of the rotation of the fan right before the fan. This just leads to system effects, and it's very unpredictable. So you have to really pay attention to the ductwork around your fans. All right, next slide. So fans depend on their inlet and outlet because that's the way they're tested with straight linears and straight outlets in the lab. And if you have extreme changes like we talked about on the inlet or the outlet, it will give you what they call system effects, which is a reduction of the capacity of the fan. And it's really unpredictable as to how much that would be. All right, next slide. If you ask the fan guy, he wants an infinitely long piece of ductwork on the front of his fan coming into the inlet, and then an infinitely long piece on the outlet to allow that pressure to redistribute, because the pressure coming off of the outlet of a fan has a very high velocity oriented to the very outer edge of the fan. That's not possible, I know that. So next slide. You want to help minimize any of these problems by putting in turning vanes, or, I know your ductwork sometimes has to be where it is, but you can add turning vanes and help minimize your system effect problems and your pressure drops. Well, the one on the right there is just in a crazy elbow that somebody wants to do. By putting in those turning vanes, you might save somewhere around 2 to 3/10 of an inch of pressure. Doesn't sound like much until you add that to 300,000 or 400,000 ACFM, And remember that equation, volume times pressure divided by 6362 divided by that efficiency. Just think of the horsepower you just saved with just some plate and a little bit of understanding of what you're trying to do. Next slide. But like I said, inland hour conditions are key. You know, the more you can stay straight on the inland hour fan, the better the fan will perform. But if you can't stay straight, go to the next one. Always remember to turn in the direction of rotation. That way you're not changing flow rotation on the fan, causing a tremendous amount of disruption and causing system and size effects. All right, next one. The next thing to do when you're doing ductwork, and these are just general rules of thumb, minimize the number of cross-sectional areas. You know, we're not dealing with a non-compressible fluid here. We're dealing with a compressible fluid. You know, you go in some of these new homes and plumbers go wild with elbows and changes and all that, and that's fine because it's pretty much non-compressible. But in a fan system or a duct system, anytime you have a cross-sectional change in area, which you're going to have because you're literally piping to your equipment, you're going to have a pressure loss. Anytime you converge or diverge, you're going to have a pressure loss. Reduce the number of turns. Every time you have a turn, pressure loss. When you have to turn, try to use turning vanes. Use big radiuses in your elbows. And here's one that's very key. Try to limit your aspect ratio. Try not, 1-to-1 would be better. Try not to go past 4-to-1, because what happens is, next slide, let me show you what happens. Next slide, we're not going to get into that. What happens here is, if you don't limit your aspect ratio, you get a lot of surface area or perimeter for the amount of area that you have in the shape, like the very bottom one. All that surface area creates skin friction or loss. So by far, you see a lot around that work. The reason you do is the most optimal way to transmit fluid. Square is fine. That's at 1-to-1. Aspect ratio 4-to-1, the next one. And then the last one, I'm just showing you 10-to-1, very poor. So try to stay either 4-to-1 or better, or around. Next one, we're not going to get into this. Every fan you have should have a vibration monitor or at least a switch on it, every fan. If you can only afford one, put it on the inboard bearing or the drop bearing in the horizontal direction. If you don't know how to set the arm up and the trip up, we would recommend 0.3 inches per second arm, 0.5 inches per second per trip. If you bought a fan from us, it'll be on the general arrangement drawing. And the reason I say this is this will save you a lot of grief and a lot of heartache. If you're monitoring your vibration, you should be able to prevent losing a fan for some unknown reason. Sick fans have symptoms. All right, next slide. Proper operation and maintenance. So I'm going to go into this a little bit about don't let your fans blow your money. And we have made a business out of upgrading fan equipment. And I want to give you some examples here, and hopefully you'll find a place in your facility that you can help. And what we're looking for are these things. If you got a severely dampened fan, in other words, you rarely ever open it up, it's a candidate to do something to improve that. If you're motor limited or capacity limited, if you got an old antiquated design, in other words, you're running a radial blade fan in a FD service, you may want to consider upgrading. If you've got severe wear issues, it may not only be just because you got a lot of particulate there. You may have a fan that's grossly missized. If you're replacing your rotor anyway, might be an opportunity to upgrade it. If you got poor ductwork, might be a way to get 1 or 2 or 3 inches back for almost nothing. If you got wide swings and loading, or you got pulsing, or you got complaints from the operators, please talk to me. Send me an email. We'd love to help you. All right, next one. These are the basic fan laws here. Why I'm showing you these is this is if you're sizing a fan, and by that you're kinematically and geometrically sizing up and down. Q is volume again, V is diameter, N is speed, and P sub A, P, the scripted P is power, and the row symbol is density. Sometimes go to the next slide. But if you've got an over or undersized fan, you may want to consider tipping or detipping that fan. And it would follow these laws here. The volume and pressure would vary by the square of the diameter change. If it's not an airfoil and you've got a fan that's grossly oversized, we can just detip that fan some, get to where your damper can open up, lower your horsepower substantially, because if you see, it varies by the fourth of the diameter change, the fourth power of the diameter change. So, and you may have to tip a fan out. And if you're fan limited, we got some motor, there might be some things we can do there. It's not always just a major fan change out. Sometimes it can be a slight modification that would dramatically help you. All right, next one. So this is kind of what I'm trying to tell you here about increasing diameter or tipping, and it can be done in the field. You can get more flow rate if you got the horsepower to do it. And conversely, next slide. Detipping the rotor may allow you to be able to open the damper up and run more smoothly, get some of the power back. All right, now I'm going to go into some of the upgrades that we did. We did one of the first ones I ever did way back early 2000 was for a cement plant in California. And at the time they were paying 8.2 cents per kilowatt hour. And California Edison had offered them an incentive on power savings. And they had worn their fan out. So I had a guy call me, he's an old friend of mine. He said, hey, what can we do here? Let's go to the next slide. But this was the fan. The original design was back in the early 80s. It was a preheater ID fan, a radial blade. At that time, that was the state of the art. That's what people were doing. And so you had 275,000 ACFM, 40 inches, 2254 brake horsepower. That was what it was designed for. Well, we went out and measured this fan. And we found out, well, he's up his ante. He's running at 329,000 ACFM, and he's lowered his pressure. And we found out he had changed a lot of things in his preheater tower that had allowed him to lower his pressure. Good thing. So go to the next one. And he was, we went out and did this elaborate evaluation where we're doing all this fan testing in the field. Next one. And these are the parameters that we're after. Velocity pressure and static pressure. We use velocity pressure to get to, the flow rate, temperature, relative humidity, any CO2 in it, static pressure to traverse, and static pressure around the fan. We also today would do a static pressure profile of the whole system, fan rotational speed and motor and power. And we go measure all of this. And we do it per one of these codes. And normally we'll do it just to the 203 code, the very first one. The others are available. We can do these. A little more sophisticated, a little harder to do. And that's AMK 803 and PTC 11, ASME PTC 11. And back in the day, before we had the advent of CFD modeling, we would do physical models. So we went out and did all this testing, and then we built a model of his housing, about a 4 scale, and we built a model of the fan that we wanted to put in there to upgrade his fan. And this is a test apparatus. Go to the next slide. And this is kind of schematically how it looks. Fan, some stiffeners, and then there's, if you see on the right side, there's a throttling device there. And that's kind of our system. So go to the next one. And this is how you make a fan curve. By using that throttling device, if you'll notice, the first point we would have measured would have been, we would close the throttling device all the way in, no flow, where you still get potential pressure. You get a static pressure at 0 flow. And then we move out and we get a 25% flow and 50% flow by opening up that throttling device, taking a volume, a static pressure, and a corresponding horsepower. All right, go to the next one. In reality, when we do this, we get a lot more points. Normally we generate 18 to 24. We have curve fitting techniques that we use, and we use either cubic splines or sometimes we use ordered polynomials. All right, next one. Well, this is what it's all about here. We took the little prototype on the left, and using the fan laws, because we were geometrically and kinematically the same, we scaled the little prototype up to the actual size. And that's how we came up with a new fan in their existing housing that would improve the efficiency at the new points of operation. Next one. And we were in the advent of computational fluid dynamics. We were able to do some of this for us. I can tell you straight up, if someone's telling you they can predict fan performance quantitatively with fluid dynamics, they cannot. They can qualitatively. If we know where we're at, then by making mods to the model that we have, we know where we can go to. But we have to have that physical data, and anybody else would too, because fans are different. Now, there are some turbine people that can, but fans are different in the fact that there's a lot of potential for separation losses, recirculation. I mean, just a ton of reasons you can't do it. But anyway, it is a great tool. to be able to, once you have a starting point, to help you in the process. All right, next slide. So, picture worth 1,000 words. Here's what happened on this fan out in California. The original fan was, as you can see, was a pretty high peaked curve. That was the setup for the 275,000. Yeah, you go. 275,000 at 41 inches. But he only needed 31 inches, and he was moving 330,000 ACFM, which he loved because he was doing a lot more production. But they were further out their fan curve, and they were very inefficient. So we went from that radial blade design, we went to backward curve design. We right-sized it. You can see the dotted green curves that we drew. They represent the new fan in the existing housing. And now it's back more of its sweet spot. So we matched the new system resistance with a new rotor, and we got this pressure drop. And that's kind of the magic of this. Next one, go to the next slide. So here's where we went from. We went to a new design from a radial blade to backward curve, IP30. We met its conditions. We went from like 2,300 something from 2,400 to 19. We saved 420 brake horsepower per fan. There were two of these. 536 horsepower, $536 per horsepower per year at that time. $225,000 in savings per year. Go to the next slide. The fan at that time, the cost of the project, total all in, new rotor and installation was $195. The savings was $225. The payback was 316 days. California Edison put in 50% of that. So the payback was less than a half a year for that project. And they've been running since 2002, saving all that. Here's another one, for example. This is a ferrosilicon plant. This started out as a wear issue. And we go up there and we find out that his fan is severely dampened. He's been experiencing vibration issues, wear, cracking his housing. It was a terrible deal. For years, we tried to get this old plant manager to let us upgrade his fan. And all he wanted to do was buy a bigger motor. And I'm like, Bobby, you don't need to do this. And finally, Bobby retired. And the day after, or the week after Bobby retired, we went back up there when started talking to the new plant manager. And that's when we got to do this upgrade. Go to the next slide. Now, bear in mind, he wanted to buy a bigger motor, and he was already burning up 1,750 horsepower. The old design there on the far right is the stats for it. When you look at the new design, we went from running 1,200 down to 900. We gave him the flow rate, actually gave him more than he needed because he wanted to upgrade. Matched the static pressure to what he really needed. Went from using up a full 1,750 horsepower motor. He was going to buy 2,000 horsepower motors. And we're now running at 492. At the time, TVA, the plant power cost was 5 cents a kilowatt hour. So the fan operating cost went from over $500,000 per fan to about $150,000 each. And that's times 4. And TVA paid for half of that. So it was a great project. So the end result was energy savings, and in less than a half a year, they paid for everything, not including the maintenance they were doing. They were spending just about $100,000 a year with a new rotor every year. Now that hurt us because we were the ones selling a new rotor every year, times 4. But he really came out, and not only today, people are beginning to talk about reduced carbon emissions. Well, that's a lot, almost 8,000 metric tons per year in CO2. Next one. This is a real showboat for us as well. This is Steel Dynamics over in Columbus, Mississippi. 4 big baghouse ID fans. They were wearing their fans out on a regular basis too, but we also knew they had some efficiency problems. So we got involved with them. We actually brought this project to them. Next one. So kind of when you're doing this kind of fan, this is not an electric arc furnace. It's more based on averages. So the average fan efficiency was just under 41%. Average fan breaking horsepower, each fan, there's 4 of them, was 2512. Well, we went in there and redid all these fans. We actually replaced the housing on these. And we went from this to the next slide, to 72% efficiency average and 936 per fan, well over 1,000, almost 1,500 per fan, and horsepower savings. And we did a lot of studies on wear. We learned how to particle track on wear. We were able to improve his wear life substantially. Case history there. If any of y'all are interested in that, we can share more results on that. But we literally went from wearing out every 6 months a fan to this was at 24 months. Now those fans have been operating over 5 years, 6 years now, with almost no wear, and they're still the same rotors. So all new rotors, no significant wear, reduced power tremendously, 25 million kilowatt hours for the whole deal. Savings are $1.4 million per year. Total cost of the project was around $5 million because they went and changed housings and they changed VFDs, and TVA put in $2.5 million into that project. They paid for that project in less than 2 years, and it's now just a gift that keeps giving. Next slide. So this is kind of the summary of the payback, and it was huge. Same thing here. They greatly improved their wear life. And these are intangibles. They had constant maintenance issue that they eliminated. They had a foundation problem. We helped them fix that. And they were constantly enforced outages. Time's money. Here's one, and I promise you this is the last one. Here's one that started as a noise problem. My buddy called me and said, I got to do something. MSHA's going to shut me down if I don't fix my cold mill fan. What's wrong? They're way too loud. So we said, well, we want to come out and look at them. We want to test. So that's what we did. And there's kind of the summary of that. We went out and did all these testing, and this one's kind of a story. That's we did a static pressure profile of their whole system, and we found this 20 inches of pressure loss. So I go into the control room and I'm like, there's a damper up here and it's got a 20-inch delta across it. Is there a reason for that? And they're like, we don't even know there's a damper up there. I'm like, you gotta be kidding me. I said, no. I said, so you never modulate this damper? No. So this damper's always where it is. Yes. We took that damper out. We went from 28.9 inches the fan was producing. It didn't need 8 because there was a 20-inch, artificial drop that they had created back in the 80s. We went from, it's a V-belt drive, we went from running that fan 1188 down to 933. We went up in efficiency. We went from $130,000 to about $24,000 in operating costs per year. The noise went away. And this was times 4. There were 4 of these. Huge, huge savings. Total payback was less right of the year. MSHA went away. They didn't have MSHA problems anymore. And, just from testing and being smart, going from a radial blade to backward curve, improving the fan, also taking out system resistance that they didn't need, we saved them a lot of money. So huge, huge deal. One thing I do want to talk to you guys, I know we're going to run short on time here, is one thing that's gotten lost over time is in leakage. And in leakage is that solid rubber. Because what happens is when you begin to develop, leaks in your system and stuff, you're pulling all this extra flow in. Well, it limits your capacity in your fan, but it also, you're paying for that. You got to pay to move that flow that you don't even need. You got to pay for the pressure requirement to move that flow you don't even need. And you can get corrosion from localized cooling and condensation. So in leakage becomes a major problem. Go to that next slide. And here's kind of why that formula I dwelt on. When you add in the fact that now you've got not only your original volume, now you've got original volume plus lost volume or lost flow rate that's trash, plus all the pressure it takes to move it, all that, and your tremendous amount of horsepower being lost to in leakage, and it limits your capacity. So we're just about done here. The last thing is talk a little bit about monitoring and maintenance. Every year I'd recommend that you guys go through planning. You probably do some type of PM vibration study around your fan equipment. That kind of triage gives you an insight to your fan, teaching you which fans may need new bearings. Once you come down, you check lubricants, you go through all your fans. You can do this with your slew bearings on the run. You can take samples. So there's a lot of things to do in outage that I would do every year. You may already have a program for that. That's good. Next slide. And just be smart. Go and try to go. There's some people that you go to a site and they'll open up a fan and it's worn out. I'm like, well, what was it last year? We don't know. We haven't been in this fan 4 years. Don't do that. At least try to get in every fan every year or every outage. And then just, take a look. Tighten down all the bolts. Check the dampers for wear. Inspect the ground areas. Follow the clues because I always say that sick fans have symptoms. Always. All right. So the theme of that is proper care is everything. And if you've ever I've been to some fan failures, and here's one where the housing was blew apart, the wheel blew apart. And you went to this group of people and they tell you that they were doing everything right. And it goes to the next slide. This was an old Greenfield fan. Kind of here's the, we're missing some slides.
Okay, well, that's okay. We can incorporate them when we
Yeah,
distribute.
we will. This one here is a steel mill fan. What he's showing you right there. This is a story here. The operator lost his fan, or lost his plug to his fan, and he lost his amps on his fan in the middle of the night. And he sent a person out to check on his fan, and the fan was out there spinning away with nothing left but the center plate and the fan was still running, but everything else was out in the yard. The fan literally blew up. Thank God nobody was hurt. Tore the housing to pieces. And this was because they didn't monitor the center plate, and that fan fell from a center plate. They monitored, they did everything right on the blades, but they weren't monitoring the thickness of their center plate. So that one failed as a result of that. Go to the next slide. This is kind of this is back to the one at the sugar mill. Go to the next slide. Next slide. Right, go to the next slide.
Alan, sounds like we had another question here. If you don't mind, we'll jump in with that.
Okay.
Here we go. Another question from Serena Bosch. Do you recommend hard-facing pulp industry IDFD and transport fans to increase life from erosion? If so, what should be the wear plate's life to schedule for a replacement in those cases?
Hey, if we were going to do wear pads, it would be really depending on how aggressive his wear is. There's different techniques we can use. I never like to put like hard facing on the blade itself, but I like to use wear pads, and they can either use, depending on how aggressive the wear is, they can use an AR plate, or they can use a chrome carbide, or even a complex carbide if they've got. And it all really gets involved because when you start adding stuff to a fan wheel, you got to take into consideration, you're adding weight, so you're lowering your fan shaft critical. You're adding stress to your rotor. You're adding WR square, which is inertia. So if you're trying to start across the line, you got to take that in consideration. But I'm all about adding wear pads or some type of wear solution. Sometimes it's as simple as adding partial wear pads and maybe some spore beads, because you don't have the additional WR square ability that the motor would need to start the fan. So there's not one answer to this, but if you'll send me an email, or we kind of see what your situation is, we'd love to get involved with you. It's not an answer, but it is.
Will those wear pads?
All right here.
Will the wear pads increase the fan?
Yeah, this one is what I wanted to talk about. When we went to a fan failure, and the guy told us he was doing everything right. He told us he was putting wear pads on every year. Problem was, he wasn't taking any of his old wear pads off. And so the fan finally, that's 5 sets of wear pads. And that was a crazy disaster that should have never happened. And so we wound up replacing this fan. It came a long way. This one is one that was a brand new installation. And we got called in. It was down in Puerto Rico. and the fan literally disintegrated. It's amazing that somebody didn't get hurt. And yes, that column is bent. Go to the next one. This was the shrapnel that came through the stack. These were blades that came through the stack. And this was, go to the next slide. This fell for this reason alone. The original manufacturer who made it did a very poor job. It was not made in the US. And go to the next slide. Where you can see where the blades were attached. They were very poor welds to begin with. They were cold welds, and they were not full penetration welds. And that should have never got out of someone's shop. That fan ran about 7 days, totally disintegrated. It was a cement plant, put the guy out of business for about, I think we built him a wheel in about a month, well, about 3 weeks, and got him back online. We actually set up the ocean barge, and the next thing I know, he had hired a Russian transport. They picked it up in Atlanta and flew that rotor to Puerto Rico. The flight cost more than the rotor did, but he'd been down. So the whole message here is, that it takes more than good fan equipment to make a good fan on installation. And a maintenance program and monitoring and proper operation are so critical. You don't want a failure. I've been to enough of them. You don't want to. Thank God we've never had a new fan fail. I just knocked on my wood, but it happens. We do see it. That's my presentation, guys.
Alan, thanks very much. Another question from Ian here. Do wear pads reduce the fan capacity?
As far as performance, no. No, they will not. They do, you got to be careful, like I said, by adding them, because it may create a problem in starting the fan if you're starting across the line. Now, if you're starting in VFD or steam turbine, it just changes the way you ramp up in speed, and you can probably do it. But, depending on how aggressive the wear is and what type of fan you got, we can recommend wear pads or wear solution.
Very good. Thank you for this presentation, Alan. It was very informative. We do have another couple of minutes left in our scheduled time frame. Are there any questions from the audience for Alan?
My
Yes, sir.
email address is on there. My phone numbers are on there. You're more than welcome to call me, email me. If you got situations or questions, love to try to help you.
Yes, sir. So it looks like a question from Alan at Crofton.
Hi, yeah, thanks. Just wondering, you said you had some operations in Canada. Where would that be? And is that who we would deal with our Canadian mills?
So our Canadian entity is where I'm based out of in Toronto, Ontario. We have service personnel across Canada. We have service personnel, specifically fan techs in the States. So you would be dealing directly with myself, Brian Buchanan, Alan Ray. We operate as one company, regardless of that one Canadian entity or our Canadian entity being in Toronto.
Okay, thank you.
Yes, sir.
That's good. There's another question in the chat.
Oh, yeah. Thank you. Johan, very good. Is there a concern with turbulence with throttling the inlet vanes?
Oh, yes, there can be. If you are, if you're throttling down substantially, and you've got inlet vanes, there's a chance that you can get what we call vortice shedding. Most of the time, when we know there's going to be low flow situations, we'll add in a feature called dorsal fins that'll help mitigate or prevent any type of shedding like that. Now, VIVs, if they've got the dorsal fins, the only thing you would possibly get would be, possibly surging of the fan. On VIVs, even if you got an airfoil, you wouldn't stall. Now, while we're on this subject, if you got an airfoil fan and you've got multi-louver parallel blade dampers, and you get down into the 40% or 30% of dampering, there's a chance you can stall that ID fan, that if it's an airfoil. By stall, it's a phenomenon where you get a pulsation. It's the stall is the same as what would happen to an airplane when the velocity or airplane got slowed or there wasn't enough speed over the full itself, it would stall. So it would lose its lift capability. And that's what happens on an airfoil fan. It loses its lift capability, and therefore it creates a pulsing, and it's a radical pulsing. Won't hurt the rotor. It won't. It will, though, destroy the dampers and will destroy the housing around it.
Okay, thanks.
Okay, very good. Another comment from Henry. Please share your expertise about fan reliability services like vibration tests, etc.
Well, I am. I'm big on monitoring. I believe that if you monitor a fan from a vibration standpoint, and also I would monitor temperatures or bearings, then you can head off a lot of issues, and you can also begin to see deterioration of your equipment. I think my dad always told me, you take care of your car, it'll take care of you. Well, it's the same way with fan equipment. You take care of your fans, they'll take care of you. Now, I believe that by watching them from a vibration standpoint, even if you're just monitoring filter out, you can tell a lot. Now, if you're having issues, we can come in with our analyzers. They're what we call FFTs, fast Fourier transform. And what they do is they'll give you a spectrum. You can see where the movement is and what frequency it is. In other words, they'll be filtered, got like 400 filters in it. And you can see, the 1 times, 2 times, 3 times operating speed. There's a lot of signatures and characteristics that give you an idea about the health of the equipment. And that can be, that's why sometimes when we do these routes or preventive maintenance routes where our guys go in and we'll do vibration studies prior to an outage. And by these signatures, we can tell a lot about the health of the fan, whether or not you potentially got some bearing issues or you got a defective ball bearing or race, or if something's wrong in that anti-friction bearing. whether you're misaligned, whether you got wear in your teeth of your coupling. There's a lot of things that with looseness, we can pick up on that. So yeah, I'm a big advocate of monitoring, both continuous and doing some pre-chase prior to outage, but it gets you ready for outage.
Okay, very
Thanks
good.
so much.
Yeah, so thank you. Thank you. First of all, Henry, thanks for helping set this up. Alan, thanks very much for the time. And this was very informative. I hope everyone found it useful. Thanks for everyone in attendance. And we'll distribute a copy of this presentation and make a recording available to everyone. So with that, appreciate your time and thanks very much.
Yeah, guys, I know we went through a whole lot here, so if you want to drop me a note or something, please do.